live stream program, we are joining you at home, representing the Museum of the Rockies. My name is Jamie Augst. I'll be your host. I'm the Outreach Program Manager. And Scott Williams, our Field and Lab Specialist, will be joining us to teach us more about how we get our collections from the field to the museum. I'll turn it over to him here in just a little bit. As you can tell, like I said, we're working from home. So if my dogs decide to sound the alarm, I'll apologize in advance. They're hanging out with us here today. The museum is temporarily closed. We're working to find out when we go back. Before we get started, I want to talk about a couple of important things you'll want to know about using Zoom. You have two ways to interact with us today. One is that chat box that you just used to type in where you are from. Thank you for doing that. The second is the Q&A box. Any questions you have for us along the way, go ahead and type them in there. Scott will either answer them within his presentation, or if we have time, we'll try to answer those at the end if we didn't get to some of them. Do try to type them in the Q&A. The chat box can move so fast that we miss stuff. The second, like I just said, is the Q&A box. Type those questions in there. Feel free to ask those questions or, yeah, any thoughts you're having, type them on in there. We're happy to engage with you about what you're thinking. After today's program, we'll send an email to teachers about more programs that we have lined up, or for you to let us know what you'd like to see in the future. Feel free to give us that feedback. We love accommodating your classroom needs. I'm going to take you on a little adventure and show you where in Montana we're at, and then I'll turn it over to Scott. Thanks again for being with us today. All right, there we are. We're about 80 miles north of Yellowstone National Park and 300 miles south of our friends in Canada, in the beautiful and historic Gallatin Valley on the campus of Montana State University. There's the entrance to our museum. It looks like fall in that picture. Let's practice using our chat box. Can you tell me what kind of dinosaur you're looking at right there? Oh, we've got T-Rex galore. All right, good guess, everyone. There's our
good job, everyone. Good job. I think most of you will probably know that this is a little clip from everyone's favorite movie, Jurassic Park. So you get a big roar if you pick T-Rex for Big Mike that sits outside. You're going to hear me at the end of my spiel say next slide. So don't be alarmed. That's me just letting Jamie know we're going to move on to the next slide. So next slide. Well, who am I? You don't need to memorize all this stuff. My name is Scott Williams. I'm the Paleontology Lab and Field Specialist here at the Museum of the Rockies. I've been here for about 3 years. Worked at the Burpee Museum of Natural History in Rockville, Illinois for about 14, 15 years before that. I've got quite a bit of field experience. Started going out in the field as a kid, as many of you probably have, going out collecting fossils in kind of my backyard. I've done field work in Utah, Wyoming, Oklahoma, Montana for about the last 20 years. So I have quite a bit of experience. Co-authored a few papers and a few documentaries. So I've been around the block a little bit. The pictures that you see here of me looking very, very Captain Morgan-like are in two different geologic formations. The top one is in the Morrison Formation of Utah, and the bottom is actually Makoshik State Park here in Montana. So next slide. We're going to go kind of on a little walk through some of our exhibit space, our paleontology exhibit halls at Seedable Dinosaur Complex. This is, for those of you who've been at the museum, this is kind of outside our fossil viewing lab where you can see our preparators working on fossils. Next slide. This is the Hall of Giants. There's a lot of things going on in this exhibit space. Right here from this picture, one of the dinosaurs that you see right off the bat is our own Big Al, famous, probably the most famous Allosaurus known. It was one of the most complete Allosauruses ever known. It lived about 150 million years ago in what's known as the late Jurassic period. Large predatory theropod. The theropods are the meat-eating dinosaurs. Kind of on the left of the screen, you can see some leg bones and a rib to a big long-necked dinosaur. These are the apatosaurs and diplodocuses. We also have some marine reptiles in this exhibit space. There's a lot of cool specimens in here, so when the museum opens back up and it's safe to come out, I certainly encourage you guys to come out and check out this hall. And there's a lot of specimens, and take your time going through it because there's a lot of information in here. Next slide.
Scott, how many fossils do we have?
Oh, well, that's a good question. So when it comes to individual fossils, so that would be anything from a little gar scale, a little fish scale or fish vertebrate, all the way up to this T-Rex that you see in front of me here. We have upwards of probably 400,000 individual specimens. Now, in the case of the T-Rex that you see here, the Tyrannosaurus Rex is a complete Tyrannosaurus Rex, has about 290 bones, 287 bones total. And each one of those bones is an individual fossil, of course, but then we will assign a number, what we call a collections number, which represents the whole specimen. So in some cases, we'll have one number that represents like this animal here, which has hundreds of bones. So we have 400,000 plus individual fossils, and upwards of probably 15,000 specimens like you see here. And this picture that we're seeing right here is part of our Hall of Horns and Teeth. This hall is almost entirely late Cretaceous, latest Cretaceous, from fossils from the Hell Creek and Lance formations in Montana. So we have Tyrannosaurus rexes in here. We have a gross series of Triceratops, the three-horned dinosaur, duck-billed dinosaurs, armored dinosaurs, crocodiles, fossil turtles, so on and so forth. It's very impressive. As soon as you come around the corner, you're going to basically come face to face with Montana's T-Rex, which is about a 40-foot long Tyrannosaurus rex from the Hell Creek Formation. Next slide. So here's an artist's reconstruction of Tyrannosaurus rex. We're going to talk about T-Rex just a little bit here. Partly because it's the most famous dinosaur ever. It's probably the most famous animal ever. I mean, it's one of the few animals that people know the species name for, Tyrannosaurus rex. Rex is a species name, and this is some artwork by Nobu Tamura that's been loaned to us. And I think it's probably the most popular dinosaur amongst dinosaur fanatics. And as I mentioned earlier, we find it in a certain geologic formation. Next slide. You want to go back one, please? There we go. So reason I kind of focus on Tyrannosaurus rex is that a lot of times in movies like Jurassic Park and other TV shows, sometimes you see dinosaurs all lumped together as if they all lived at the exact same time. And that is just not correct. For example, Tyrannosaurus rex lived at the very end of what we call the age of dinosaurs, the end of the Cretaceous period, 66 to 67 million years ago. The big long-necked dinosaurs like Apatosaurus and Diplodocus lived around 147 to 150 million years ago. So you can see they did not live at the same time. An Apatosaurus and a Diplodocus would have never, ever met a T-Rex, and vice versa. And something that may blow your mind is that we, human beings, are closer in geologic time to Tyrannosaurus rex than Tyrannosaurus rex was to Diplodocus and Apatosaurus. So that gives you an idea of how long dinosaurs were the dominant animal on the planet. It's really a phenomenal story. Next slide. Well, back to our Hall of Horns and Teeth. Can you go back one? Go back to the left. Or
I'm struggling here. Bear with me, folks. Thanks for your patience. This guy?
Nope. There. Stop. Okay. Well, we're back at the Hall of Horns and Teeth here, and this is our Cretaceous up. Here's our T-Rex. In the bottom left-hand corner, we have a very large adult Triceratops, the three-horned dinosaur. And then to the right, we have the duck-billed dinosaur Montosaurus. They all are from the same time period, the same locations, basically the same geologic formation, the same geographical areas. From the Hell Creek Formation, as I mentioned, stuff that is 66 to 67 million years in age. How do we find them? Now, next slide. Well, according to the movies, it's just like this, right? If you watch Jurassic Park and you watch, there's some TV shows and series, whatever, all you have to do is brush away an area and there's a complete, in this case, Velociraptor, just waiting for you to just pluck out, right? Well, as we go along here, you're gonna realize, if you don't know already, that is not how this works. Very, very, very rarely do you find sites where the skeleton of a dinosaur or other fossil animal is just perfectly articulated in a real soft sediment, like a really soft sand, where all you need is a brush and there you go. There are some instances that are close to that, but they are very rare. So next slide. There'll be a test on this after this, just so everyone knows. This is, kidding, of course. This is a geologic time scale. I think some of us have seen some of these. And for you kids out there, as you go through your schooling and you get into classes like earth science, stuff like that, you'll see a generalized version of this. And generally speaking, as you're looking at your screen up in the left-hand corner, those time periods are closer in time to us. Very top of that is basically modern. And as we go down to the right, we get older, farther back in time. This is 4.5 billion years old, and our fossil record is a pretty small percentage of that amount of time. And so we're going to be focusing, because we want to look for dinosaurs like Tyrannosaurus rex, Triceratops, and Admonosaurs, we're going to be focusing on the very late Cretaceous. So if you move the cursor over here to the Cretaceous on the left, you'll see right there at the, down here, a little further down right there, basically there's a line where it just stops. And that line marks an extinction period where about 70% of everything in the fossil record goes away. So T-Rex, Triceratops, Admonosaurus, the flying reptiles, the pterosaurs, the seagoing marine reptiles, even types of invertebrate fossils, fossils that don't have backbones like ammonites and types of coral, they all go away. It's a very important time in our history, and so that's why we do a lot of work and focus on that time period. Next slide. There's some certain principles that paleontologists and geologists apply when we're doing field work, and when we're looking for rocks. Obviously, we've got to find the right kind of rocks to go looking for dinosaurs. Like right where I am at now in Bozeman, we have rocks that are too young, that sit above rocks that are far too old, and or the wrong kind of rock. So these are basically laws, things that govern the work we do, and they make sense, right? So if we look at the top right-hand image there, the oldest rocks are at the bottom or below the younger rocks. Does that make sense? Because of the way sediment deposits. So if you mentally visualize a river 100 million years ago, and as the river is moving along, it's dropping little particles of sand and clay and mud, that forms a layer. And then weeks go by, months go by, another layer forms on top of that, and on top of that, and on top of that. The oldest stuff is on the bottom. And when this stuff is deposited, it's all just deposited horizontally. So like this, okay? You know, very rarely do we get deposition that's at an angle or, you know, bowed. Everything gets initially deposited horizontally. Then because of mountain building processes, other processes, that will buckle or get pushed up. And then we should be able to trace these layers. For example, if you're in a valley and you go to the north side of the valley and you find a sandstone there, you should hopefully be able to go to the other side of the valley and find out where that layer picks back up again. The valley, of course, is where erosion has happened, where rivers or rain or some other force has been breaking down the rock and creating the valley. So those are kind of the three things that we focus on when we do our paleontology work, and helps guide us. Next slide. Fortunately, one of the things that makes paleontological fieldwork a lot easier to do today than, let's say, 100 years ago, 150 years ago, is that most of our states, like in this case, this is a state map of Montana, have had geologists out working, looking at the rocks and mapping them and determining what formations are there. So if you go to the western part of the state, which is the left side, you find a lot more rocks that are associated with building of mountains, so igneous and metamorphic rocks. As you go to the east and northeast, you'll find more areas where there's been deposition, ancient deposition of ocean beds and rivers and lakes and things like that, that create the sedimentary rocks that we like to find fossils in. So Montana is very geologically rich. We have lots of formations here. We have especially a lot of the Cretaceous period, the end of the age of dinosaurs. We've got some Jurassic, which is a little bit older, and we've got a lot of Cretaceous. So basically the last 15, 20 million years, we've got a lot of it. Next slide, please. So we're going to focus on one particular area, the Hell Creek Formation, because like we started this adventure looking for, say we want to look for Tyrannosaurus or Triceratops or the duck-billed dinosaur mosasaurs. We're going to look in the Hell Creek Formation. And the Hell Creek Formation, which represents the end of the age of dinosaurs, is found over eastern Montana. So if you see where it says Fort Peck on the map there, there's a big body of water kind of in the northeast part of the state. It's at Fort Peck. The Hell Creek Formation is found around there. If you go east to Glendive, it's found there. If you go south to Ekalaka and Broadus area, it's found in that area. And we're going to focus right now on the areas near Ekalaka because that's where I've done a lot of work. And so that star kind of generally represents where we're going to do some prospecting on. We're going to do some fossil hunting. So why don't we head there? Next slide. Well, one of the things that we, oh, go back. Okay. One of the things that we, oh, back.
This one?
Yes, the world. If we were to go back in time, if we were to take a time traveling ship, go back in time and go around the Earth, we would look down and we would see that our continents look quite a bit different. 66 million years ago, our continents weren't as far apart from each other as they are now. You can see that Africa and South America are much closer. Europe and Asia are much closer to North America. But what's really interesting is that you have these seaways, what we call epicontinental. It's a big word, but basically just means seaways that go over the continents. And if you look at North America, up in the left-hand side of the globe here, you can see that there's a body of water going right through the center of North America. One time it went all the way up through Canada. And areas like Montana and the Dakotas at this time were coastal. So they were more like Louisiana, Alabama, northern Florida. It was warmer and wetter. It was more tropical. You had rivers and streams that were basically emptying into this body of water. So areas in eastern Montana were much warmer and wetter. Next slide. And if we take a look at, this is an artist rendering of what it would look like if we took our time ship and landed. If we landed here in eastern Montana 66 million years ago, this might be a scene that we would see. At first, we would get out of our time ship and we'd see some trees that look kind of familiar, things that kind of look like magnolias and pine trees or conifers and some cycads and things like that. And in a little bit, we'd have a Triceratops walk out, or we'd have a T-Rex, or we'd have other small dinosaurs. You can see a little Archaeoraptor, or raptor-like dinosaur to the left, and you'd have crocodiles and turtles. And you would realize that this environment, what we call a paleo environment, was much warmer and wetter. And this river that you see the T-Rex and the Triceratops on is depositing sediment. When it floods, when it rains and floods, it picks up all that sediment, sandstones and sand and mud and clay, and then deposits it in it around over its banks. Next slide. And that sediment that was deposited 66 million years ago eventually becomes rock, mudstones and sandstones and shales, and becomes what we call the Hell Creek Formation. And here in this picture, you can see what the Hell Creek Formation looks like now. Totally different than that other picture, right? This stuff, every time it rains, it freezes and thaws, the rock breaks down and weathers away, erodes away, and exposes sediment, new sediment, and bones. Next slide. Here's a bigger picture of the Hell Creek Formation. This is actually, I took from one of the highest points in the Ekalaka area. And all of the area that you see to the left and in front of you that doesn't have grass or sage on it, that's all the Hell Creek Formation. In fact, a lot of that grass and sage is covering up some of the Hell Creek. There's more of that formation below. Now, one of the questions somebody may ask or may have already asked is, why is it called the Hell Creek Formation? Well, geologic formations get named typically from the location that they were first described. And there's an area up near Fort Peck, Montana called the Hell Creek. And that's where these types of rocks were first identified and formally described. And then we realize that that formation expands all over eastern Montana, even into western North Dakota, western South Dakota. So for those of you who might be in the Colorado area, the Morrison Formation is named after an area in Morrison, Colorado. And that the same goes for areas in the Midwest and East Coast, places like that. Next slide.
How big is Hell Creek? Can you?
Well, for square miles, I couldn't really give you, but basically, you're talking about probably hundreds of thousands of total square miles, because again, it surrounds the Fort Peck area. It goes to Glendive. You have it in the Glendive area, and it goes south through Baker, Montana, into Carter County, and then over into the Dakotas. So it takes up a lot of space. So, which is good for us, because the more of this formation that's available, the better our chances are of finding good fossils.
And do you ever find fossilized grass or plants?
Yes, we do. It's a great question. Do we ever find fossilized plants? Yes. In fact, one of the ways we can reconstruct this paleo environment is that we find fossil leaves. And so we have a good idea of what sort of trees and other plants were in the area 66 million years ago. And there are all types of trees that live, well, they're not all trees that live today, but many of them that have relatives that live today live in very warm, wet, lush environments like we see down in the Gulf Coast states, Georgia, Louisiana, Alabama, Florida. So again, that's one of those things that tells us that 66 million years ago, eastern Montana did not look like this at all.
And how many dinosaur bones have we found in Montana? Do you know?
Oh, total bones, probably thousands to tens of thousands of dinosaur bones, if not more.
Great. Thanks for those questions. We have a lot of questions. We'll try to get to more of those as we continue. Thank you, everyone.
Next slide. So what do we do? How do we find bones? We just basically walk around these exposures. You can see this There you can actually see there's some students here. We're walking around, we're looking for these bones that weather out or are exposed from erosion. Next slide. Here's a bone that I found just kind of sitting out. It is a leg bone to a duck-billed dinosaur called a Montosaurus. And this is how I found it, just exposed. You can see it's cracked up. That's because of erosion and weathering. Well, I wanted to collect it, so how do I collect it? Next slide. Well, you can see what I've done is I've dug around the bone. I've created kind of a pedestal. I've trenched around it with a rock hammer and some picks and awls, and I've made kind of a pedestal because I'm going to get ready to plaster jacket this. But this is the first step. Next slide. I've covered the bone with a separator. In this case, it's wet paper towels. Sometimes people use tin foil or even newspapers and things like that. But this is what you would put on here because you don't want to put plaster of Paris right on the bone. It's going to damage it. Next slide. Here I have, after I put the separator, I've taken burlap strips that we dip in plaster of Paris. We've wrapped the whole bone and we've created a plaster jacket. Then what I'm going to do is I'm going to dig underneath it and roll the whole thing and do the same thing the other side. Next slide. Here's a picture of one of our Montana State University students, Tom Labarge. He's at a site where he's found another Edmontosaurus tibia. That's the shin bone. And you can see again, he's dug around it, trenched around it. Here we have it plastered. But there's a problem where this particular bone was found. Next slide. It was up there where that big yellow arrow is. And from there down to the ground was 184 vertical feet. So we had to figure out how to get that bone down. In its plaster jacket, it was well over 100 pounds. And you can see how steep the sides of these hills are. So us picking up each end and just walking it down probably isn't going to work. We thought about using a stretcher, but we're in the same kind of situation where if one of us slid, we would go quite a ways down the hill. So in some cases, you have to improvise. Next slide. Yeah, this was me after we found that bone up there because I knew we had to bring it down, but we had to figure out a way to bring it down. And that is part of field work. You have to improvise. You have to, you know, if you get knocked down, you got to get back up and figure out a way to get that bone safely out of there. Next slide. Well, in this case, you know, we weren't going to bring in a helicopter for an individual leg bone. And there were some of the hills that were, there was just enough slope that we could lower it down using rope and just sliding it down. So that you can see I'm lowering it there. You can see that one of our students behind me he's holding on to me. There's a rope holding on to me. You know, it wasn't so steep that I was worried about going down. And of course, if I started to lose my hand grip on that, you know, I'm not gonna dive over the hill and catch it. We'll just let it slide all the way down because we're, you know, concerned about our safety first. But we slid this down, then we come down the hill, pick it up, walk it over to another slope like you see here, and lower it down again. The whole process took actually about 2-3 hours just to get it down to where we could walk it out to the vehicle. You don't see this on Jurassic Park, just so you know. Next slide. Well, as I said, bones were to a duck-billed dinosaur called Allosaurus, one of the more common plant-eating dinosaurs from the late Cretaceous. And, you know, like I said, we're out there looking for Edmontosaurs, Tyrannosaurs, and Triceratops. Next slide. Well, I'm going to talk to you about a Triceratops site that was found in 2018 that we've been working for the last couple of years called the Captain Chuck site. Here's a arrow showing roughly where it is in the Hell Creek Formation. Next slide. Here we have some of the very first pictures. You can see that in the center of the picture, there is a bone sticking out of the hill right there. It has eroded away. There's actually a bone kind of up and to the right as well. It's a little harder to see. It's a very flat bone. But we went and looked at it, realized that that was a femur, the upper leg bone to a Triceratops, and the flat bone over to the right is actually part of the head shield, the frill. So obviously there appears to be a dinosaur coming out of this hill in the same layer over several feet. But you can see that we have rock over top of it, which is called overburden. We got to get that down. So next slide. Here we are removing the overburden. Again, this is kind of the unglamorous stuff. We're using picks and shovels and rock hammers to remove the rock over top of it because we have to get down to that bone layer. Next slide. Once we did get down to the bone layer and we started switching over, we stopped using rock hammers and heavy tools and started using picks and awls. This is Dr. Yoshi Katsura. He's a paleontologist from Japan. And you can see his hand, he's got a little sharp instrument there. It's called an awl. He's using a nice fine brush in his left hand. And what you can see here is several bones. This animal is not put together like the velociraptor you see in Jurassic Park. It is kind of blown apart. A lot of times, this is how you find dinosaurs. We call this disarticulated. The bones are not together. You can see some ribs to the left, part of a head shield right in front of Yoshi's head, and then to the right, a really cool big horn. That's one of the big orbital horns to a Triceratops. Next slide. Here's one of our other student volunteers, Whitney, and this is from this year. Again, you can see a big bone jumble, a bunch of ribs. There's actually some hip bones. The big bone right in the center that's kind of going up to the right, that's the other femur. So we found the other big leg bones. And so we had to get that out because it was, again, you can see all these other bones all around it. And so we had to carefully remove a lot of these bones. Next slide. We have to map everything. So this is an important part of the science. We have to map these bones in relationship to each other. So we take grids, we'll measure the lengths of the bones, we will measure how far they are from a fixed point. We'll actually use surveying equipment to figure out how deep down in the ground they are and even at what angle they are. Are they laying completely horizontal? Are they tipped up? Which direction are they pointing? Next slide. And then, of course, we plastered it. As we mentioned before, we plaster these bones. We just don't carry them out. And in this case, we decided to plaster that big femur and several other bones together. We used a piece of wood. You can see a 2x4 to help reinforce and strengthen the jacket. Next slide. And then we had to haul it out, which, again, can be quite a distance. We're lucky that the Captain Chuck site is within, 1,000 feet or so of a Jeep trail. So it's not like we had to hike this particular specimen out several miles, but sometimes you do. And that can take the better part of the day. The upper left-hand corner is a big leg bone that we took out from another site that we're carrying. And that was a full mile from where our vehicle was through lots of valleys and gorges and hills. So that took over half a day just to get out. Next slide. And as I said, these are bones to a Triceratops, which is the most common dinosaur in the Hell Creek Formation. And probably next to Tyrannosaurus Rex, probably the most famous and recognizable of the dinosaurs. Next slide. Well, once we bring all that stuff back to the lab, we've got to open it up and work on it. And here we have several of our volunteer student preparators here, and they all have different dinosaur projects to work on. But we will basically take a saw, open up those plaster jackets, and start using a variety of tools to prepare them. Next slide. One of the tools that we use quite a bit are pneumatic or air power tools. These are basically miniature jackhammers. And I actually have an example of one here, which you can see, I'll put up to the screen. They run off air, so we hook them up to air hoses. And then this part here, this tip, works like a little jackhammer and helps remove hardened sediment away from the bone. We call these tools air scribes. We use them a lot. Next slide. We use a variety of hand tools. You can see on the left we have dental picks. If the sediment is very soft, we'll use those. We'll use tweezers and fine tip awls. And you can see some brushes down the left. We will literally brush sediment off the bones. We also use the brushes to apply glues and hardeners. To the right, you can see some glues that we have prepared here. One of the things that we will put on a bone once all the sediment is off is a substance called Vinac, and I have a jar of it right here. It's a made-up word, Vinac. We basically take little plastic beads that we dissolve in acetone. Then we'll take one of these brushes and brush it on the bone once it's completely clean. This will dissolve into the bone and help harden the bone up and basically help preserve it. So it's an important process, and that allows us to handle the bone a little more safely. And then, because we're not done with the bone once we've put the glues on it. Next slide. Here is our senior preparator, Carrie Ann Sell. She's working on that femur, that Captain Chuck Triceratops femur. There you can see she's using a hand tool to remove the sediment away from the bone. It's a type of mudstone, so it's kind of soft. And right next to that bone was a rib and a pelvic or hip bone. Next slide. Here we have, this is another tool we use, an air abrasion chamber, and this is one of our students using microscope so we can see that we're not damaging the bone. And basically what we're doing is we have a little nozzle, gun nozzle in there, where we more or less sandblast these bones with a soft powder like a baking soda to get that thin veneer off of the bone. There's a little layer of sediment, mud, or sand on there. We will sometimes use this to get that off. But we want to use the microscope along with it so we don't damage the bone. And this allows us to see up very close to make sure that we're doing this right. Next slide. Here I am using the pneumatic tool. I'm working on a dinosaur. This is actually a tail, an articulated tail to a Thescelosaurus, which you'll see in a second. And I'm using that. These are the bones that come off the bottom of the tail where muscles and tendons would attach. And so you can see I'm using a magnifying lamp to get in close. And I'm basically removing the rock over top and outlining it. Next slide. Here's a picture of the whole Thescelosaurus. You can see there's a partially articulated tail, hips, right leg and foot. The left foot's just kind of coming out. Here is the torso and the chest, the right arm, and you can see the cast of the skull there. But this is a nearly complete dinosaur from the Hell Creek Formation. Thescelosaurus, next slide, is a relatively small plant-eating dinosaur. It lived alongside Triceratops and T-Rex and Edmontosaurus. Next slide. Once the specimens are completely prepared, we will make plaster cradles for them so they can rest comfortably and not break under their own weight. So here I am getting ready to get this specimen ready for a cradle. In the bottom right-hand corner, you can actually see a plaster cradle underneath. That's a new cradle. So it can sit like it is right now and not worry about breaking apart. So we cradle these bones before we go into collections with them. Next slide. And this is our picture of me doing a 3D scan of a mammoth skull. You can see I've got this weird kind of joystick in my hand. And what I'm doing is I'm basically scanning this bone, all the surface detail that you see, which goes into that computer, and it builds a three-dimensional model in the computer. So we're moving away from molding and casting fossils like we used to do for a long time. If a researcher in, let's say, Berlin, Germany, contacts us and says, I'm studying mammoth and I'd like to look at your skull, but I can't come there, we can scan this, send him a file on a computer where he can look at all the details without even having to come here. So that helps that helps streamline science. Next slide. So I've gone through a lot in a relatively short period of time, field work and lab work. So there's a lot of planning and work that's involved in field work, from prospecting to excavating to transporting it back. Can take several weeks or even several months or sometimes multiple years to get a dinosaur out of a quarry. And then once back at the museum, it can take a very long time and many people working on a project to get it completely prepared. A complete dinosaur skeleton or a near complete dinosaur skeleton could take tens of thousands of hours to prepare each of the bones, to scan them, to make cradles, and so on. So, so when you see movies and you see them literally find a dinosaur and get it out, that's usually science fiction. This is the reality. So field work is fun, lab work is fun, but it takes a lot of work and takes some patience. I'm going to take this opportunity to thank everybody for coming out. We've got plenty of people to thank, including our Bureau of Land Management, our state parks, Department of Natural Resources, and our MOR crew. So last slide is some cool stuff that's coming up in the near future. We've got some streamable learning stuff happening on Thursday, April 30th, reptiles and turtles and tortoises. We have on May 1st, primate evolution with my friend Amy Atwater.
Great. Thanks so much, Scott. You guys had a lot of great questions. I'm sorry we couldn't get to all of those. There's a lot that goes into getting those bones out of the ground into the museum. So thanks, Scott, for sharing that with us. Like Scott said, we look forward to seeing you next week. And yeah, we'll see you then. Keep learning, keep asking questions, and have a great day. See y'all soon.